So our next aim will be to get some applications of this whole theory of characteristic classes in Riemannian geometry. And in fact, we will mostly focus on the four-dimensional case, because in the four-dimensional case, many things simplify a lot. On the other hand, it's still interesting enough to give us non-trivial results. But before I get there, I have to first study the algebraic properties of curvature tensors in a bit more detail, because all our characteristic classes are obtained by some algebraic procedures out of the curvature tensor. And so we have to relate this to our more commonly known concepts of curvature in Riemannian geometry, such as scalar curvature, Ricci curvature, etc. So let's do that today. And since these considerations are of independent interest and in fact in all dimensions, I'm not focusing on 4 dimensions today. Only when I get to the applications, maybe on Thursday, I will restrict myself to 4 dimensions. So today, let's do some algebra. Algebraic curvature tensors. So basically, we will study tensors on a fixed Euclidean vector space, and which has all the symmetries that curvature tensors of a Riemannian metric have. And we will see what the structure of this space of algebraic curvature tensors looks like. So our setup will be that we start with an n-dimensional real vector space, V. And of course later, V will be the tangent space to a manifold at a certain point. But now for the moment it's abstract. And so the first thing I want to define is an encoding of the Bianchi identity of curvature tensors, which gives rise to the so-called Bianchi map. So what is it? It's a map from fourfold tensor product of V star. So tensor for 0, 4 tensors on V to itself. And what does it do? So it maps an element in here, which I call R, again to an element in here, which will then be V of R. And since this will be an element in here, I want to consider this as a 4 linear form on V, so I insert 4 vectors in V. And I'll tell you what the result will be. And the result is it's a symmetrization procedure. So what you do is you keep this last entry fixed and you commute the first three. You take R of x, y, z, t plus R of, now we have y, z, x, t plus R of, now we have z, x, y, t. So this averaging procedure, which for all x, y, z, and t in V. So that's my definition. That's the Bianchi map. Well, and so what are the properties of this map? And if you remember that if this was the Riemann curvature tensor of a Riemannian manifold as a 0,4 tensor field, so you lower all indices, then vanishing of this expression is exactly what we call the Bianchi identity. So we will be interested in the kernel of this map, where the Bianchi identity is. But anyway, so for the moment, so what are the properties of this map? Well, first of all, it's a projection. So b squared is equal to b. So let's go through that. And in fact, well, what do we do? So if we apply b and insert these arbitrary vectors, then we get this expression. Now let's apply B again. So what will happen? Then we get another factor of 1/3, and each of these three terms is again permuted in the first three entries. So the first one then gives rise to these three, but if we again permute the second one, we also get these three terms, and if we permute the third one, we also again get these three terms. So we have 1 on 9, and then 3 times these three summons in different order. And so therefore we get this. So trivial. Good. Alright. Now the next thing is that this map B is GLV equivariant. So what does that mean? Well, here we have this n-dimensional real vector space, and certainly the group G and V, so invertible isomorphisms of V, act on V, and therefore they act via the congruent representation on V star, and this induces an action on this tensor product. And the claim is that the map B commutes with this action. So let's just compute it, and we see that this is also not easy. So let A be such an automorphism of V, then so what do we have to check? So we first apply A to R and then apply B. Now I want to show that this is the same thing as first applying B and then A. And so let's check this on the 4 vectors. Okay. Now we have to insert the definition. So this is 1/3, and then we have to take AR of xy zt plus the other two terms. Right. And now the action induced on these tensors by the action of A is actually acting on V, so it is acting on these x, y, z, and t. And how are these actions related? Well, the action here is defined as given by the action on the entries except that if I did it this way, then this induced action would be a right action. Right? If you take another A prime and you apply it to it, then here the order of the A's would be flipped, and therefore we would get a right action. But one always wants a left action, and for this reason one takes a -1. Then we get a left action again. So it's given by the dual map of the inverse. That's called the contra-gradient representation. And here there's the other three terms. Okay? And now of course we see that this is nothing but VR of R applied to these 4 vectors. Which is then nothing but A acting on B of R applied to the original vectors. And this is this equivalent property. This is important because it tells us that this map is not, will not depend on any choice of basis or anything. Good. That's good. What else do we have? Well, here's the image. And now I want to apply this map to not the whole space here, but in fact I've applied to a subspace, and the subspace is lambda 2 V star and then symmetric product on that. So what does this mean? So what is this space? This is the space of 0, 4 tensors, which is anti-symmetric in the first pair and in the second pair. And where, so let me just write it down explicitly here. So this is the space of all R's for which we have the following symmetries. So that refers to skew symmetry. So we consider this basically as a map from two vectors to two vectors, a symmetric map from anti-symmetric two vectors to anti-symmetric two vectors. So that means that the thing is anti-symmetric in the slots of the first pair. But it's symmetric if I interchange pairs. And from that it follows that it's also anti-symmetric in the second pair, because you can interchange without sign, then interchange within the first pair with a sign, and then interchange back without another sign, which you see then it's also anti-symmetric in Z and T. So if you like, just take this as a definition of this subspace. And now if we apply our Bianchi map to the subspace, what's the image? Well, the image is the space of totally anti-symmetric tensors. Which is totally anti-symmetric in both slots. So let's see that. Alright, so let's see. If let R be in the subspace, and we want to check that B of R is totally anti-symmetric. And so that means if I insert 4 vectors and interchange 2 of them, I get a sign. Or equivalently, if I put in 2 equal vectors somewhere, I get 0. And so we have to check that now. So for instance, if we put in x and then z equal t as an example, so what will we get? This is by definition 1/3 times r. So let's just write down the definition. Then we have x z t plus r of x z x t plus r of z x x t, right? And now we see, since we are in the subspace, this means that this curvature vector, algebraic curvature vector, if you like, so is antisymmetric in these two slots, so that guy vanishes. This is because R lies in this space. That's one of the symmetries that we have here. And here, if we interchange the 2 first, then we get here, if we interchange the first 2 slots, then we get this one. But if we do that, again by this symmetry property, we get a sign. And therefore these 2 terms cancel. So we get 0. And the same thing if you equate any 2 others entries. Of course, going through all possibilities now. Similarly, for other cases of 2 identity entries. 2 identity entries. So this shows that B of R applied to the space is contained in the space of totally symmetric tensors and totally antisymmetric tensors. But now, we already know that the B is a projection. And so what I'm claiming here is that this is the image. So in order to prove equality, we simply take one vector here and insert this into the B and see that we get doesn't change, right? So that R now be in this space. And then what happens if I apply B to it? Okay, let's just write it down. 1/3 R of x y z t plus R of y z x t plus R of z x y t. Okay. So this one is the one we are looking for, and I would like to convert this into that one too. So what do I have to do? I have to put the x on the first slot here. This means two interchanges, which gives me a plus sign. Then I get this will then be the same as that. And similarly here, in this case, I have to put the z to the third slot. So again, the z has to be interchanged with x and y. Gives me two signs, so no sign. And so these three terms are individually the same. And therefore, this is R of x, y, z, t. In other words, each vector here in this totally antisymmetric space is actually the image. Namely, it's the image of itself. So therefore, B of R of this space is actually equal to as claimed. I mean, this is a subspace of that, right? If your thing is totally antisymmetric, then it will certainly be antisymmetric in the first two slots, also in the third and fourth slot. But if you interchange the pair, then you have to do two interchanges and again two interchanges, which gives you no sign. Maybe I should have said that, right? So obviously, lambda d star is a subspace. If this was the question. Good. Okay. And the last property is that, I mean, a priori, B is a map from all four tensors to four tensors. Then I've restricted it to the subspace. I have computed the image of this. And then, by this remark that we just had, this is contained in that space. So in particular, this bitmap B is an endomorphism of this subspace, right? With this image. So that's just what we need. Good. Now I'm ready to define the space of algebraic curvature tensors. Definition. Namely, so CV is by definition the set of all algebraic curvature tensors in the satisfying these symmetries. Antisymmetric in slot 1, 2, antisymmetric in slot 3, 4, symmetric in pair 1, 2, and 3, 4. And in addition, it should lie in the kernel of B so that the Bianchi identity is satisfied. Right? So in other words, it's the kernel of the Bianchi map restricted to this subspace. And this is called the space of algebraic curvature tensors. Good. And it's, of course, it's clear why it's called that, because these are the tensors that have exactly the symmetries that we know from from the curvature tensor of Riemannian geometry. Good. Now let's see if we can compute the dimension of this space of algebraic curvature tensors. This can be helpful, as we will see later. So let's do that. And how can we do that? Well, since the space is given as the kernel of a projection on that space, and we know what the image is, what we need to do is we have to take the dimension of this space minus the dimension of that space. Right? And these two things we can compute. So let's do that. So first of all, let's start with lambda 2 star. The dimension of lambda 2 star. V is n-dimensional. What is it?
N over 2?
Yes. N choose 2. That's what it is. Now, so in other words, n times n minus 1 on 2. And now we want to have the dimension of symmetric endomorphisms of that space. So if I call this temporarily capital N, so we have a capital n-dimensional space here. And so what's the dimension of symmetric endomorphisms of the capital n-dimensional space? So these were the anti-symmetric endomorphisms, the skew-symmetric endomorphisms. Here are the symmetric ones.
Like the symmetric tensors of the n-dimensional space has to be 10 times n plus 1.
Like this one, except with the plus, and we have to take the capital N, right? Exactly. So this is capital N plus 1 on 2. And now we insert this value of capital N into it. Then we have n minus 1 times n minus 1 plus 1. And then we have, so we have a 2 coming from here, we have a 2 coming from here, which gives me a 4 here, and then there's another 2 here. Okay, so that is what we get, so let's simplify that a bit. So then we get, we have sort of n minus 1 here, then what's that? So this will give me, we have an 8 here, this gives me n minus 1 plus 2. So n squared minus n plus 2 on 8 times n minus 1. Alright. So that is the space of this space. And now what is the dimension of that space? The dimension that we will have to subtract. Of course, we know that is n choose 4. So which is n minus 1, n minus 2, n minus 3 on 4 factorial, which is 4 times 3 times 0, that is 24, right? Okay, so let's compute the difference. So therefore, the dimension of my space of algebraic curvature tensors is the difference. So that is the dimension of the whole space in which it lies minus the dimension of the image of the projection, whose curve we are looking at. So that is, as we just computed, the first one is this guy. And minus 1 plus 2 on 8 times n minus 1 minus n minus 1, n minus 2, n minus 3 on 24. So what do we get? Well, we have an n minus 1 here and also there. And then I need a 24 in the denominator, so I multiply this by 3. Then I get 3n squared minus 3n. sorry, 3n squared minus 3n and plus 2 times 3 is 6. No? And this guy goes here, and this is multiplied by 3.
You miss an n.
There's an n here, yes. Thanks. Minus, and then I have to subtract that part. So n times n minus 1 is already here, and then I have to just these two things, so which is n squared minus 5n plus 6. So you check that I don't make a mistake. So which is what? Well, the 6 cancels, that's good. Then I have 3n squared minus n squared gives me 2n squared, and I have minus 3n plus 5n gives me plus 2n. So we can cancel the 2, and we get n times n plus 1 here. So altogether we get n plus 1 times n squared times n minus 1, 12. That's the formula. Okay? Good. Alright, so that is one map. And then we can already anticipate, so the Yankee map. So this gives rise to our space of curvature tensors and curvature tensors. But then in Riemannian geometry, we know Ricci curvature and scalar curvature, so let's get that into play. So this gives rise to the next definition, namely the Ricci contraction. Another map named by an Italian mathematician, the Ricci contraction. And this is basically what we know, namely, so let's see, then this goes again from this space here. And ends up in symmetric 0,2 tensors. And so R is being mapped to C of R, where C of R applied to two vectors. So that should now give me a symmetric bilinear form. And it's defined the way you know how, as the Ricci curvature is defined by tracing 2 of the 4 slots in the curvature tensor we are contracting them with light. So that is the sum. Yes. And I should say for this, I have now to assume that it's not just a naked real vector space, but rather now it has to carry a dimension. So I forgot to say that. So from now on, V is an n-dimensional Euclidean vector space. We didn't need this so far, but now we need it. Because we now, in order to do this contraction, we need the metric. And I can formulate it like so, that I just take, be careful with the sign convention. This way. So I use this trace where E1 up to En is an orthonormal basis of E. And of course, orthonormal makes only sense if I have a Euclidean vector space. Now you may argue, well, the way I know Ricci curvature, the tracing is done over the second and third slot, not the second and the fourth one, which gives exactly the opposite sign. Or alternatively, the tracing is done over the first and the fourth slot, which also would give me the opposite sign. This depends actually on your favorite convention of the curvature tensor. So when looking at the curvature tensor as a 1,3 as a 1,3 tensor, we use the convention curvature tensor is this, right? So that was our convention for a curvature tensor as a 1-3 tensor. And then, if you want to apply this to 0-4 tensors, you have to make sure that your so now I want to write it like so. So that's really a different R. So maybe I distinguish on writing R's twiddle here for the usual curvature tensor as a 1-3 tensor. Then you could write this as scalar product of that curvature tensor T and a minus sign here. Or alternatively, people sometimes use the opposite sign convention here, and then there's no sign here. If you could also leave out the sign, and then you would trace over 2 and 3. Whatever, right? So, but that's the convention I'm using now. Just fix it once and for all. Alright, so anyway, then this is consistent with the definition, with the usual definition of Ricci curvature. So if you apply this to the curvature tensor coming from the curvature of a Riemannian metric, and then this will give you exactly the Ricci curvature as a 0-2 tensor. That's why it's called Ricci contraction. Is that clear? Yeah. Good. And now remark. So this Bianchi map had several properties, and in particular, we observed that it is GLV equivariant. That's no longer true for the contraction map, but the Ricci contraction map is still equivariant with respect to the orthogonal rule. So remark, C is OV, and let me call the metric Q. So with scalar product Q. So Q as a bilinear form. So then these are the invertible linear maps that are compatible with the preserved Q. And with respect to this subgroup of GLV, it is equivariant. If you look at the definition, this becomes clear, because if you first apply your automorphism to R, this means, or let's say you apply to C of R, then this means you have to apply the transformation to X and Y. So you have to apply it to X and to Y. But since it's an orthogonal map, you can also apply it to this orthonormal frame, because then this will give you another orthonormal frame, and the definition is independent of the choice of orthonormal frame. And then you can drag the thing out. So this is obvious. But it will not hold for non-orthonormal transformations, because then this will not, the image of an orthonormal frame will no longer be orthonormal. For example, if you take 2 times the identity, then this will give you, this will not. All right, good. Yeah, this is the Ricci contraction. And the last thing we need, the last operation, is the so-called, goes in the opposite direction. So the Ricci contraction takes such a 4 tensor and converts it into a 2 tensor. And now we have something which goes the opposite way, and that's called the Coulthard-Ninomiso product. And this is the following map, noted by a wedge, encircled wedge. And this goes from, takes 2 symmetric endomorphisms and gives me a 4 tensor. Let's do defined as follows. If I have two symmetric endomorphisms, or two symmetric linear forms rather, H and K, then I should get such a thing. So let me evaluate the four vectors. And now this is defined as follows, and I have to check the signs. So I have options now. I always take two of the four vectors, insert them into one of the two bilinear forms, and multiply and do this in a certain linear combination. So let's see. I have to take H of z times K of the other two, which is y and t, plus, now I take H of y t times K of the other two, which is x and z, minus H of xt times K of the other two, which is y and z, minus H of yz times K of xt. So that's the so this map is called Fulcrani-Nomiso product. Okay, and well, properties lemma. First of all, the thing is symmetric. It's a symmetric product. So the Fulcrani-Nomiso product of H and K is the same thing as the product of K and H. Well, what happens if we interchange H and K? If we interchange H and K, then this first term gets interchanged with that term, and this term gets interchanged with that term, and these have equal signs. So nothing changes here, so we have the symmetry, it's obvious. Good. More interestingly, our Fulcrani-Nomiso product actually always lands us in the space of algebraic curvature tensors. And for this, we have to check the symmetries that we have used to define those. So let's see. Here we still have the space, so we have to check the Bianchi identity and also the symmetry and anti-symmetry in the various slots. So for example, let's check anti-symmetry of that thing in the first two entries. Okay, so I could argue, okay, I checked that when I insert twice the same vector, then I get 0. That's equivalent. So what happens if I do that? Well, then I get, so I just everywhere I have to replace y by x. Maybe I can do this with the y-pin technology, but I want to keep that formula. So if so I would have an x here, and an x there, and an x here, and an x there, instead of the y. Now we see here we have xt, xt, xz, xz, so these two terms cancel, and similarly these two terms cancel. I do that. So this is why it gets red. I can remove that again. And so we have that. What else? We have to check what happens if I interchange the pairs, right? What happens if I interchange the pairs? xy gets replaced by zt and vice versa. Well, if x and z get interchanged and y and t get interchanged. So if x and z get interchanged, here nothing happens, here nothing happens. Similarly, here nothing happens, right? If these two get interchanged, and here nothing happens. So the first two terms remain unchanged. And now here, if I interchange x and z and y and t, then this gets replaced, x gets replaced by z and t gets replaced by y. So this becomes zy, which is exactly this term. And similarly, this gets replaced by this term. So these two terms get interchanged. But the whole expression remains unchanged. So this shows by inspection that we certainly have that. So that means or we are already landing in this space symmetric to tensor of lambda 2 of V star. And the last thing that needs to be checked is the Bianchi identity. So if we apply the Bianchi map to this Cardinal-Meso product and we evaluate the result on 4 vectors, what will then happen? Well, we have to take this expression here and 1/3 of it, and then permute the vectors x, y, and z in it. So we have 4 terms for the first one, unpermuted, then we get 4 terms for the first permutation, a cyclic permutation, and then we get another 4 for the last cyclic permutation. So altogether we get 12 terms, with 6 of which have positive sign and 6 of which have negative sign. And then if you spell it all out, you see that one with a positive and one with a negative always cancels, so everything cancels out. So that's a straightforward computation, which I really don't want to do now. It's an easy exercise. Straightforward computation gives you stuff. And then we have that. And of course, that's the reason why we are interested in this Cardinal-Meso product, because it lands us directly in the space we are interested in, the space of algebraic curvature tensors. Now, there's a canonical symmetric bilinear form on our space, namely the metric itself. I call it the metric Q. And if we take this bilinear form and put Cardinal-Meso product with itself, we should get something canonical. Right? This is the metric and symmetric bilinear form. So this should give me some particular element in here, some canonical element in here. And so what could that be? Well, remember that the CV is a subspace of this space. And using the metric, this is canonically isomorphic to symmetric endomorphisms of this space. So let me write it like this: symmetric endomorphisms of this space. We use the metric for this identification because we actually need this product with its adjoint and with its dual space for that, right? And metric can be used to identify those spaces. And if we look at it from this point of view, then of course we immediately see a canonical element in here. Symmetric endomorphisms of some vector space, there is something canonical in it, namely the identity. The identity map. And in fact, this is essentially the identity map. In fact, it is 2 times the identity map of lambda 2 V star when we use this isomorphism. And so let's check that. Yes, indeed. And in fact, when we check it, then we also see that, because so if I tap, so this is the identity of this guy on this space. But now I want to consider it as a 0-4 tensor, so I insert x, y, z, t, right? Because I want to compare it with this guy. And under this identification, what is this? This is this identity map applied to the covector coming from these two. Scalar product with the corresponding vector here. And this is the induced scalar product on this space, which is induced by T. Like so. Okay. So here I'm using this identification. Because now, of course, this makes sense to talk about the identity here. So what we get is, it's just the identity, so it's x wedge y, scalar product z t, wedge t. And now we have to remember how we actually induce a scalar product on lambda 2 from Q. And it's as follows. I have to take the scalar product of the first of x with z times the scalar product of y with t minus the scalar product of x with t times the scalar product of y with z. Okay, so that's what we have. So this is how the scalar product is induced by Q. Alright, and we have to now compare this with the concurrent product which we have here. Good. So now both h and k are just Q, the scalar product. So they're both the same. If h and k are the same, then in fact also these two terms are the same. And these two terms are the same. And the first ones give me this, and the other ones give me that. But here they appear twice, which is why this is only 1/2 of Q concurrent meso Q applied to x, y, z. And this is where this factor 2 comes from. Good. And there's one more thing. Yes, the last property, which is of importance to us, is if we take concurrent meso product of Q with some linear form H, and then do the Ricci contraction, what you get, then you get some, so we start with this bilinear form H, tensored with the canonical form Q, and contract again, so then we get some new bilinear form. It should somehow depend linearly on H. The whole thing, this is concurrent meso product is linear in both cases. C gives me a linear space, so it should be some linear, somehow dependent on H. And it's not directly H itself, as you might suspect, but it is n minus 2, n is dimension times H, plus the trace of H times Q. That's the right formula. But in any case, it's something canonically computed out of the bilinear form H. So let's see what that is. Alright, so C of Q concurrent meso H applied to two vectors x and y. We need to compute that. So by definition, this is the trace of Q concurrent meso H applied to x, EI, y, EI, where EI is an orthonormal basis. And now let's spell this out. So that is the sum of, now we have to use this formula here, where I replace k by h and h by q. So we get q of first and third is xy times h of the other two plus, here I have q of second and fourth, which is EI, times h of the other two, which is x and y, minus q of first and fourth, which is x comma I times h of the other two, which is second and third, which is EI comma y. minus q of, and here I have to just interchange these two, so it's ei y times h x y. Alright. Well, what will this give us? So here this one gives me the trace of h times q, right? So this is the trace of h times q of xy, which is this term that we have here. Now here, if I trace the metric itself, then I just get the dimension. So this gives me n times h of xy, which is not quite what I have here, but I have two more terms. Minus, now if I look at this thing and I insert this scalar q of x comma ei into the h, then what I have here is the expansion of the vector x into this orthonormal basis. So this term gives me h of x comma y. And similarly, if I insert the q term into the h on the second slot, then the second slot is the expansion of the vector y in the orthonormal basis ei. So this gives me another h of x comma y. And that's the formula. Good. That's what we have here. And now I'm aiming for a decomposition of this space of algebraic curvature tensors into subspaces, which are actually then OQ submodules. And before I can prove that, the last preparation here, common lemma, namely, if the dimension is at least 3, so 2 dimensions is somewhat special. This is particularly trivial actually, but in dimension at least 3, the map that I get from taking symmetric bilinear, so 0,2 tensors, symmetric 0,2 tensors, to algebraic curvature tensors, where I send k to the Corbani-Nomiso product with k, with the metric, with q. Right, so that's a canonical linear map I can look at from symmetric bilinear forms to algebraic curvature tensors. And in fact, this map is injective. And it's the adjoint, or actually 4 times the adjoint, equals 4 times the adjoint of a map in the opposite direction, namely the Ricci contraction. The adjoint of C, going in the opposite direction. In other words, we have identified the adjoint map of this one as that. So let's prove that. And let's also see why dimension must be at least 3 for that. All right, so first, injectivity. Good. So okay, so let q concurrent Nomiso k be 0, and we need to show that k is 0. Right? And why is this true? Good. So let's fix the vector v and 0. And now I'm looking at vectors in the orthogonal complement of that vector. So let x and y be both perpendicular to z. And I'm going to derive something about the bilinear form k of this orthogonal complement, so for these two vectors x and y. Good. And well, what do I know? I know that the Kuhani-Lewisian product vanishes. That is 0. And I insert for any choices, for anything that I can insert. I'm inserting z, x, y, z, for instance. And now let's spell out what that means. Here we still have the formula. And then we get, so again, h gets replaced by q, and k is exactly k. So then we have q of first and third, which is z and y, times k of the other two, which is x and z, plus q of. Now I have to interchange these two pairs. Minus q of, and now I have to take first and fourth, which is both times z, times k of the other two, minus q times, and now I have to interchange, right? Times q times k times z. Well, now let's see. We have x and y are both perpendicular to z, so this guy is 0, y is perpendicular to z, and similarly this guy is also 0. And z is non-zero, so we can get that term. The whole thing is 0, and so we can divide by this term and solve for k, x, y. So therefore, k of x, y equals minus, then I have k of z, z divided by q of z, z times q of x, y. So that's what I have. Z is fixed, and this holds for all vectors x and y in the orthogonal complement of z. So in other words, so that is a certain constant, so I can write this as a constant depending on z times q of x and y. So in other words, k is a multiple of q of the metric, and at least on the orthogonal complement of z, and this factor a priori depends on z. So we have that. So this holds on z, right? So I've concluded. And now if I take another vector z, so let the tilde in V with R0 be another vector, then we can play the same game, of course, and we get that k is also equal to a constant depending on this other vector times q of the orthogonal complement of that vector. And now we use the fact that n is at least 3. Because that means if you have two vectors, then their orthogonal complements are at least two-dimensional, and they intersect in something non-trivial. So the intersection is at least one-dimensional. If n was 2, then of course, if z and z tilde were orthogonal, there would be no vector lying in both orthogonal complements. Okay. So choose x in the intersection of these two orthogonal complements, but not 0. And that's possible since n dimension is at least 3. Good. Then what we get is, if we insert this vector into our bilateral form, on the one hand, this is cz times q of x, x. On the other hand, it's also cz tilde times q of x, x. And since the vector is non-zero, the metric on x is not 0, right? So I can divide, and I can conclude that zz equals zz tilde. So that means I have this coefficient independent of z for such that k is a multiple of all of them. So this simplifies the thing a lot. And now I can go back into the equation. Namely, I know that q coparium meso k is 0, but I know now that this is c times q wedge coparium meso q, and we know that this thing is not 0 because it corresponds to 2 times the identity. So that's not 0, and therefore this coefficient c must be 0, and this implies that k is equal to 0. That's intuitivity. Okay, good. And the other thing, namely, where's the lemma? No, okay, here it is. Namely, how it relates to the Ricci contraction. So we have to compute that. I want to keep this here. That's the second part. So let's start with some algebraic curvature vector, curvature tensor, and let's take the scalar product with that thing. And again, here I have an induced metric induced by Q and induced metric on the space of 0, 4 tensors. So, and how does this metric, how is this scalar product? What does it look? Well, yeah, can anyone tell me how it looks, say in terms of an orthonormal basis? If I have two 0, 4 tensors and I want to compute their scalar product, how do I do that? Well, I take my orthonormal basis and I insert the vectors into these two 4, 0, 2 tensors, multiply the corresponding coefficients and sum over all possibilities. Right? So what I have is R of EI1, EI2, EI3, EI4 times the same thing here. Q coparium meso k of EI1, EI2, EI3, EI4. Now I sum, so that's orthonormal basis, of course, and I sum over all these pieces from 1 to n. Good. And now what do we get? The simplification comes from the second term since the q is just the metric. But anyway, so let's look at the sum R of these energies times, and now I have to spell out the coparium meso product, and that's again the formula. So what do I get? So the H is now the Q and K is K. So if I insert these orthonormal vectors into my H, I get either 1 or 0, depending on whether they are the same or not. And for this term, I have to take the first and the third vector. The first and the third one then give me a delta I1, I3, right? Times, so that's the term coming from the Q term here, times K of the other two, EI2, EI4. So that's the first term. Plus, let's see, here these things get interchanged. So here I get a delta I2, I4 times K of EI1, EI3. So the second term. And the third term comes with a minus sign. You have the first and the fourth vector, so this gives me delta I1, I4 times K of EI2, EI3 minus, and then again interchange the pairs, so which gives me delta have EI2, EI3 times K EI1, EI4. So that's what we get. And now let's see. And let's take the first summand here. So this means I only need to look at the case where the first and the third indices coincide. And so that means if I have so what I then get is the summation of EI1, EI2, but the third one has to coincide with the first one, so I get EI1, then EI4 times K of 2 EI4. And similarly for the other terms. And here, then I have summation only over I1, I2, and I4. And the other terms are similar. I'm not spelling them out. And we see we get this summation here. If we first perform the summation, which is not occurring here, and this is exactly the Ricci contraction. So this gives me the Ricci contraction of R applied to EI2, EI4. And now I sum only over EI2, EI4 times K of the same thing. And then the other three terms are similar. And this I recognize as the scalar product of this bilinear form with that bilinear form. So that's the scalar product of C of R with K. And the other three terms give me exactly the same result. This is why I get a vector of 4 here. Here it's pretty obvious because we just interchange the summation from first and third to second and fourth. Here the summation is now done over first and fourth, which is not the Ricci contraction, but if I interchange things, it becomes a Ricci contraction, which gives me a sign that cancels this sign. That's it for the last time. And so, you see, up to this factor of 4, this map is the adjoint of that map. Good. So that concludes the proof. All right, good. And now let's come to the decomposition I'm aiming for. Namely, and maybe I can, let's do this right. The theorem. So let me formulate it in dimensions of these 3. We will come to the 2-dimensional case in a moment, that's very simple. In any case, then we can decompose the space of algebraic curvature tensors into 3 subspaces, which are called UV plus ZV plus WV, where we have these spaces UV. So here I just take the multiples of metric combining mesometric itself. So that's a one-dimensional space mapped by this particular vector. We know that this is a non-zero vector, non-zero tensor. We take its multiples. So that's the first thing. Then ZV is given as everything that I obtain from Coulthard-Meso multiplying the metric with any trace-free symmetric anamorphism. So this refers to trace-free, so the 0 here, bilinear forms. And the last one is given as the kernel of the Ricci contraction intersect the kernel of the Young map. So these are this is the decomposition, and we'll relate this to classical curvature notions in a minute. But let's first prove it. All right. And we have this map. We have this map Ricci contraction, and Ricci contraction goes from our space that we are considering to symmetric bilinear forms, and we also know its adjoint. So the first thing we do is that we decompose the space CV into the kernel of this Ricci contraction map plus the image of its adjoint. And we know what the adjoint is, namely it's this cardinal Wiese product up to the factor 4, which is irrelevant here. So that's the kernel of C plus everything that is obtained by okay, let me be a bit more precise. Of course, here I'm looking at the map, the Ricci contraction restricted to a set of algebraic curvature tensors, of course, right? And similarly here, and we take its adjoint. And now, if I restrict to this, this is exactly then the kernel of B. So this one gives me already this guy. And here, we know that the adjoint of this map is given as cocardinal Wiese product with Q. That's what we just proved. Yes. So last property here. Did I erase it? No, here it is. And so this map is given by this map. That's the adjoint map. So what we have here is Q, wedge, and then all symmetric bilinear terms. So that is, the first thing is already this W space plus, and here this can be decomposed further. Namely, symmetric endomorphisms can be decomposed into multiples of the identity plus trace-free symmetric endomorphisms. So that means R times identity of the star plus trace-free. Now I'm using that the Q is injective, so that this orthogonal direct decomposition can be multiplied out if you want. So this is W plus, then I have Q, cocardinal Wiese product of that one, which as a bilinear form is just the Q itself, right? So that is that plus this guy. And this are the spaces that I've listed here. So this is WV plus UV plus ZV. That's the decomposition. Good. And we were always working with all of the equivariant maps here. Everything was all of the equivariant. Some was even GLV equivariant, but everything was certainly all of the equivariant. So that's why this decomposition that I've written down here is actually a decomposition into all of these submodules. So if you act with an element out of O of V on a tensor here, this will leave these spaces invariant. This is because they have been defined as images and kernels of equivariant maps. Perhaps one remark. It's also orthogonal, and even more, it's actually the decomposition into irreducibles. So that's what I wanted to say. So this decomposition, let me give it a name. Star is the decomposition of the O of the Q module CV into irreducibles. Into irreducible O of Q modules. So that means they are all invariant under the OV action. Since this is a compact group, they are also, with respect to natural metric, they are also orthogonal, as you mentioned. But it also says that there is no further decomposition, which would be invariant under the orthogonal group. I'm not going to prove that, and we are not going to need that, but I'm just mentioning it here. So there is no further decomposition as an O of V module. If we will restrict this group slightly and get a further decomposition in one case, but as an O of V module, it's not. None of these three spaces can be decomposed any further. So this one certainly cannot because it's one-dimensional. But a priori, maybe this one or that one could be decomposed further. All right. So now let's make a few remarks on low-dimensional cases, special cases. Let's get one. Remark. So if n is equal to 2, so then what's the dimension of the space of algebraic curvature tensors? We have computed the dimension earlier. So let's recall the formula. It's gone now. So it's 1 on 12. Yes. Let me first recall the general formula because we will, in a moment we will need it. And then if n is equal to 2, this gives 1, this gives 4, this gives 3, so this gives 12, which cancels the 12 here, which is 1, right? So that's 1. And we certainly always have this guy. So in that case, this is already everything. So the other two spaces are trivial. In this case, C of V is just 2V. So the curvature tensor is really simple. And we know this basically from classical surface theory. There is essentially one curvature notion, Gauss curvature, nothing else. And everything else, which would be invariantly defined, is just a multiple of Gauss curvature. So that's, and this is basically the prefactor that you get here. We'll see this more explicitly in a moment. Now, if n is equal to 3, what do we have then? So then the dimension of our space of algebraic curvature tensors is what? Well, we have 2 times 9, which is 18, times 4. Well, maybe we should first cancel the 4 with the 12. Then we have 18 divided by 3, which is 6. So it's 6. Furthermore, the dimension of uv, of course, is always 1. And what's the dimension of this zv part? So now we are in the case of dimension at least 3, where the q is injective, and where this map multiplied by q is injective. And that means that this space has the same dimension as that space. And now what's the dimension of that space? V star is 3-dimensional. Trace 3 by 3 matrices, symmetric ones. What's the dimension? 5. Yes. It's 5. So we've got already everything here, right? So therefore, this W space is actually 0 in 3 dimensions. It's not there. And starting in dimension 4, then we really have all the 3 components. So the statement of the theorem is still true, except that this space is 0 in 3 dimensions, and these two spaces are 0 in 2 dimensions. Good. Okay. That's nice. And now I'd like to relate this decomposition that we have here, this abstract decomposition, to the curvatures that we know from Riemannian geometry. I mean, we already know that this map little c gives us the Ricci curvature tensor. But let's see how exactly this decomposition looks like. So, if R is the curvature tensor of a Riemannian manifold at some point, and I apply the Ricci contraction to it, and I get the Ricci tensor. That's the 0,2 tensor field. And okay, and this can of course be decomposed further into the traceless part, Ricci 0. So that's the trace-free part of Ricci curvature. And plus the thing that I have removed, the trace part, which is a multiple of the identity. And this multiple is the trace of Ricci divided by the dimension times the right? So that's what we have. Because if you take the trace of the identity, you get n and not 1. So this is what I have to divide by n. Good. And this, of course, we know. So the trace of Ricci is what we call in Riemannian geometry the scalar curvature. So we have scalar curvature on n times q plus the trace-free part of Ricci. So that's what we get if we apply this in Riemannian geometry, the Riemann curvature tensor. On the other hand, we have this decomposition. So we can write our curvature tensor and decompose it into these three parts. So we get some multiple of q to prime of q plus some other thing, some q to prime something trace-free. So that's a number and that's a trace-free, what do we call it, k, or a trace-free tensor field plus some part in this W space, which I call W. And so now let's compare. Let me apply C to this decomposition. Then I get that C of R is equal to alpha times C of Q HQ, Companion meso Q, plus C of Q Companion meso K, plus C of W. But C of W is 0. Because W was the kernel of C intersect the kernel of the Bianchi map. And these things we have computed. This was one of the properties in the lemma that I thought we just erased. Namely, this formula the last formula in this lemma about the companion meso product. Now I have to find it. And let me write it down again. C of Q companion meso with some symmetrical linear form was n minus 2 times k plus trace of k times q, right? That was the formula. So that we can apply here. So this gives me alpha times. Now I have to put k equals to q. Then I get n minus 2 times q plus, and then I have to take the trace of q, which is n times q. So that's what I get from here, plus the second term. Well, here I just have to copy what I did here. So that's n minus 2 times k plus the trace of k times q, but it's trace-free. So this second term does not appear here. And that's it. And so in other words, we have alpha times, and then I have n minus 2 plus n, so this gives me 2 n minus 1 q plus n minus 2 k. So that is C of R. On the other hand, C of R is this, and then I can just compare. So the trace-free part is this one, G0 is equal to n minus 2k here. And the trace part, scalar curvature on n, is given by alpha times 2 n minus 1. Comparing these two components. And now I can go insert this back into this general formula. Solve for alpha and k, and insert this back. So I get the formula R is equal to, alpha is equal to scalar curvature on n, and also divided by 2 n minus 1. So we get scalar curvature divided by 2n minus 1 times q Quaternion product with q, plus, then I have q Quaternion with k, and k is the trace-free Ricci part except for this vector which I divide out. So I get 1 on n minus 2, and here is the traceless Ricci tensor, plus my W. And so if you know from Riemannian geometry what scalar curvature is and what Ricci curvature is, then you understand these two terms. You also understand the Riemann curvature tensor, then you can use this as your definition of the wild tensor. But it's not just some arbitrary definition, it's a definition that arises naturally from this decomposition up there. And this is how the things relate. Okay, my time is up for today, so next time I will focus on the four-dimensional case. There are some special properties there, and then we will see some applications.